So this summarizes the methodology that we use to perform the sparse modeling, sparse tensor accelerator modeling, and we're also having this implementation available in our Timeloop V2 infrastructure that allows us to implement the methodology. Here again, I think you have probably already seen this many times, both in the first part of the background and the second part of the background. This is a Timeloop V2 infrastructure that implemented the methodology we just discussed. It takes in workload mapping architecture sparse optimization feature that produces the energy efficiency and number of cycles, and as well as if your mapping is valid. I hope now all these input makes more sense to you, and how they interact each other will also make more sense to you. Internally, we have the 3 steps that we discussed before: dense modeling, sparse modeling, and microarchitecture modeling, where the first and last step is an enhancement based on Timeloop V1. The second step is the additional step that we added specifically for sparse tensor accelerators. We want to briefly talk about the inputs. So all of the inputs for Timeloop is in YAML format. As shown here is a simple example of sparse optimization specification. YAML format uses list and dictionary to describe various information. And here is just a high level how a input could look like. We will have a lot more details on how we want to specify these, what are the rules during the hands-on session with some examples. And internally at a very high level, we have been talking about all these metadata formats, all these different density models, and the actually core sparse modeling module. As you can see here, we have a pretty modularized implementation of these 3 important parts of our sparse modeling procedure, and they basically interact with each other via a pretty defined interface. So if you have some new format model, or if you're interested in some new density model, it will be very likely for us to integrate, or for you to integrate your model into our infrastructure with not a really hard time, because of the modular implementation that we currently have. And very briefly, Timeloop V2, just as Timeloop V1, also supports Mapspace exploration. So as we have discussed, you could map a workload onto an architecture in many different ways. And there is some mapping that work really good, some mapping that doesn't really work. Timeloop allows us to perform automatic Mapspace search. So in this figure, as you can see, in the Timeloop box here on the right is our 3-step modeling. On the left is the Mapspace that Timeloop is able to construct. It will construct a Mapspace with all possible mappings of this workload to the architecture. It will pick a mapping, perform the 3-step evaluation, give feedback to a searcher to see whether this is a good potential mapping. If not, the searcher will pick another one, and it will iterate through, or with a heuristic, iterate through the map space, find the best mapping, and produce the energy efficiency and cycles of the best mapping. So in this way, with the map space exploration feature turned on, you then don't need to actually send the mapping to the tool anymore, because it will do the automatic search for you. So then for the Timeloop Mapper tool, this is what we call it. So you can enable Timeloop Mapper. Then you only need to send in your workload, your architecture, and your sparse optimization feature. And Timeloop Mapper will find the best mapping for your setup. Okay, so now that we have introduced our infrastructure, we can take a look at how we can use it and what are some example studies that we did. The study that we want to show is using the infrastructure to do exploration of different sparse optimization features. We use a high-level architecture setup here, which is basically the topology for Iris V1 with DRAM global buffer in 168P array. Each PE in the array has its own local storage. In this hardware architecture setup, we want to explore how we can apply sparse optimization features. The first thing that we want to look at is DRAM compression or DRAM data representation choice. So what are some important factors that define the impact of compressed data representation format? And specifically for this study, we want to try three things. First, we can, just like what the original Iris does, we compress input activation and output activation. And this is what we call CIO. I stands for input activation, O stands for output activation. We could also only compress weights and output activation, which is CWO. We could also compress all of them. We want to see what is the impact, what defines the impact of these different ways of combining these optimizations. So first, let's see whether uncompressed traffic breakdown and compression savings have some relationship or intuitive relationship. So one of the guess people probably have is if your specific tensor occupies a huge proportion in uncompressed DRAM traffic, as shown in this uncompressed DRAM traffic breakdown, for example, if your input tensor is very significant in this breakdown, you probably want to compress it, because if you are able to compress a portion of it, it will have a larger impact on your overall traffic. And on the right, we're showing a Timeloop V2 analysis of this kind of optimization application. So in this figure, the x-axis is showing baseline, which is no optimization applied, dense workload, dense architecture. And CIO, as we have discussed, compress input and output. CWO compress weights and output. CIW compress all of them. Are three different sparse optimization applications. The y-axis is showing the normalized energy consumption, and each bar is a stacked bar of the energy consumption of the various components in your architecture. And what we want to focus specifically on is the DRAM energy consumption, which is the light blue bar here. So what we're saying is, according to intuition, we probably will save the most if we compress on the tensor that occupies the most in uncompressed DRAM traffic. So, for example, in AlexNet convolutional layer 4, inputs is the dominant DRAM traffic access, and that means we probably want to compress inputs more comparing to weights in order to save more. And although the difference is pretty slight, you can still see that we are saving more when we are compressing on inputs. But is this true? Is this correlation true for all of the layers? And the answer is no. If we use V2 to try to evaluate multiple example layers as shown here, you will see that it is not true that compressing on the tensor that dominates DRAM traffic will for sure lead to better performance. So for example, the most extreme example would be layer inception 3A pole projection, which is the second in the column in the first row, where as you can see that the uncompressed DRAM traffic breakdown is very, very significant. It kind of go to 80% in total when things are uncompressed. However, when you look at the analysis of the inception 3A pole projection layer, when we apply CIO, which is compressing inputs and outputs, compared to compressing weights and outputs, which is CW, we're actually spending more energy. And this energy is even more than baseline. So it's not true that we want to compress the tensor that dominates uncompressed DRAM traffic, and this can be shown for inception 3A 1 by 1 as well as for convolutional layer 5 for AlexNet as well. So for all of these 3 layers, compression and the dominant input tensor does not give us a better performance. The reason, as you probably can imagine, is due to the fact that the density of these tensors matter as well, and they play an important role here. So for example, for the second inception 3A pole projection layer, the density of inputs is especially high, which is 0.96. So no matter what you do in terms of compressed data representation, all you can compress is for the most 4% of your input tensor. And because of the high density, the metadata overhead is extremely high. And that's exactly the reason why when we put this sparse optimization to Timeloop V2, we can see that it's not actually giving us any saving, instead it's causing more overhead. And for the other layers, inception 3A, 1 by 1 and convolutional layer 5, it is due to the similar reason, where you actually have a denser input tensor, and even if it dominates the uncompressed DRAM traffic, it is not the best choice when we pick a compressed data representation. So as we can see in that simple example, when we play with these sparse optimization features, Timeloop V2 is able to tell us what are some important factors that decide the impact of your sparse optimization. For the DRAM compression study is both the uncompressed traffic breakdown and the tensor density that together define the impact. You probably think this is pretty straightforward. We can use our Excel sheets to calculate this. So let's look at a more complicated example where we actually want to study the impact of gating on chip. And we look at 3 examples: gating the input scratchpad, gating the weight scratchpad, and perform gating on the actual computation, which is the Mac. So let's look at what are the important factors that define the behavior of these 3 or these types of optimization. Okay, so first let's look at, now we know that density is very important. Can we find some correlation between the density of a tensor and the savings brought by the gating sparse optimization? Here we're showing the layer densities as well as a plot for inception 3A 1 by 1. On the x-axis, again, we have the baseline, gating scratchpad, gating weight input activation scratchpad, gating weight scratchpad, and gating Mac. The y-axis again is the normalized energy consumption. So for inception 3A 1 by 1, we have seen that gating input scratchpad is giving us the most significant energy saving. Now we want to ask the question: if the tensor has lower density, then this tensor should be the conditioned on tensor, meaning that it should have associated with metadata, and it should allow the other tensor to be gated based on it. For example, for inception 3A, when we gate input scratchpad, we gate it based on weights, which is stored in the weight scratchpad. And the reason why we are seeing a significant saving, it is because that our weight is only 0.37 dense, and this low density gives us a lot of savings when we perform gating and inputs. And is this true? Does that mean that for all of the layers below, for sure it is the one option where we gate based on a sparser tensor will give us better performance? For example, if we look at AlexNet Com4, is it true that we should gate on weights in order to get better performance? Gate on weights means gate based on weights means gate input scratchpad based on weights stored in weight scratchpad. And the answer is of course no. So if we look at AlexNet convolutional layer 4, what we expect would be gating input scratchpad based on weights stored in weight scratchpad gives us better performance. which is the second column, gate I scratch pad. However, as you can see, gate I scratch pad gives us worse performance comparing to gate wait scratch pad. And just to make it clear, when we are performing gating on wait scratch pad, we are associating metadata to inputs, and we are performing the gating based on inputs, which has a higher density. So why is that? Why are we gating based on a tensor that has higher density, gives us better performance? The reason is mostly because of the architecture attributes or the hardware attributes. So let's look at how the gating is performed. Originally, we have a P architecture with the 3 local scratch pads. In order to perform a gating on wait scratch pad, we need to, as I have said, provide metadata information for input activation, because the gating is conditioned on input activation. And by the way, gate with scratch pad is the third column here. So essentially, in order to do the third column, we're adding some extra hardware to store the metadata for input activation. And we'll read out the metadata for input activation as well as the input activation in order to decide whether your corresponding weights data will be gated. Now, if we want to gate input scratch pad, this is the P architecture that we need. We will essentially need to have storage for metadata for the weights stored in the weight scratch pad. As you can see that we have a larger weight scratch pad in our P architecture, so we then have to have a larger metadata scratch pad in our P architecture to store the associated metadata. And as you can imagine, the larger metadata hardware is introducing more energy per access for the metadata accesses when we're performing the gating. And this is exactly why, even if our weight has a lower density, gating based on it is not giving us better performance. And this essentially is telling us that we have to consider the hardware cost of a sparse optimization as well, because it gives us a lot of variation if you change the architecture in different ways. And you probably have also noticed that we are not doing ISO area. So for each instance, we're introducing different amount of extra hardware. So not only is your gating input scratch pad giving you more energy consumption due to the larger metadata scratch pad associated with the weight scratch pad, it is also giving us more area overhead because of the larger metadata scratch pad need to be added. So this tells us the fact that its density itself is not enough for us to determine the impact of a specific sparse optimization, and Timeloop V2 is able to help us to answer these intertwined questions based on all of the information it can gather in a systematic way. We can look at more examples. This is again applying gating on the different example layers, and one column that we haven't talked about is gate MAC only. So this is basically letting your MAC recognizing 0 operand. And you can imagine this is the way that incurs the least amount of extra hardware. And as you can see, sometimes actually outperforms the ones that introduces a lot of metadata overhead. And the reason for the specific case in section 3A whole projection is because you have a very, very dense inputs. So if you want to gate with scratch pad based on input, it really gives you nothing because of the input density. So again, you really have to both consider the density and the hardware attributes in order to analyze the impact of this sparse optimization feature, and Timeloop V2 is able to collect all these information for you. So as a summary, in order to define what is the impact of what are the important factors that define the impact of gating on chip, we have discovered uncompressed traffic, tensor density, as well as hardware attributes. As a summary of what we have discussed in this section of the background lecture, first we introduced the methodology for performing sparse tensor accelerator modeling. It involves 3 important specifications, including mapping, statistical workload density models, as well as sparse optimization features. We discussed how we could systematically perform the analysis of the interactions between these different specifications. We also then allow a modularized modeling process such that we decouple the dense traffic modeling from the sparse optimization impact modeling. We implemented the proposed methodology into what we call Timeloop V2 infrastructure. The infrastructure is implemented in a very modularized way so that it's easy for us to add, or for users to add more data representation formats as well as density model plugins. We have also presented validation and case studies. We validated our infrastructure on RSP1 architecture and SCNN architecture. We have performed exploration of various combinations of sparse optimization features and discussed what are important impact factors identified by Timeloop V2 that makes the sparse optimization feature analysis very interesting. So that summarizes the second part of the background lecture. Thank you very much.